Hi everybody, and welcome back to the next video in our series on magnetism. And now we're going to look at a second application of the Biot-Savart law. And just recall, this is what the Biot-Savart law says. We have a magnetic field that is generated by a current, and we can describe it by the calculation as shown. So now what we want to do is apply this to a circular loop of wire. So what we're going to do is we're going to orient our circular loop in the XY plane, and let's let our coordinate system look like this. And we'll use y there, we'll use x here, and z here. And let's let the origin of the circle be in the middle, and let's give it a radius a, okay? And what we're going to do is we're going to evaluate the magnetic field at a point P along the z-axis. Why are we going to do this along the z-axis? Because if we go off the axis, the integral becomes uncalculable. In elementary functions, you would have to use a computer, you'd have to write a program, do numerical calculations, etc. And you can do that, but that defeats the purposes of this example. So, where do we go from here? Well, it's easiest to start to think through how to most easily simplify this calculation, okay? And first things first, we need to define our current. So we're going to give our current a value I, and we'll let it flow in that direction. And so it's going to go around the loop like this. And one thing to note is when you have a single loop of wire and you have current running through that single loop of wire, the magnetic field, the current must be constant in that loop. If you have a closed loop, whether it's with a circuit, battery, and wire, or whether you have a circular loop of wire like this, if you have a closed loop of wire, the current has to be the same everywhere if it's flowing. That is fortuitous because that allows us to draw the current out of the integral and or pull the integral pull the current out of the integral, perhaps is how I should say that. And we're left with the line element dl crossed into the r vector divided by r squared. So the next thing to do is to define our dl and the r hat vector. Okay, so if let's go right at a point that crosses the y-axis here. So let's look at a small strip of length dl along the wire here. And if I do that, then my r vector, from which I'll draw my r hat, it's going to be along this line. So there's my r vector, and r hat is going to be the unit vector along that direction, okay? And I can immediately get my r squared value from the fact that the magnitude of r is going to equal, well, if I define my point P to be a distance z above the xy plane, then this is going to be a squared plus z squared, and therefore r squared is going to equal a squared plus z squared, okay? And this is fortuitous as well because now r squared equaling a squared plus z squared, both a and z are constant. So A is just the radius of the circle, that's not changing. The point at which we're evaluating the field, that's not changing. So R squared in this particular case is constant, and I can pull that out of the integral as well. So in this particular case, I can say mu naught I over 4 pi times a squared plus z squared. I almost started to write b squared, but a squared plus z squared times the integral dl cross r hat. Now, one thing to note, we're going to integrate over dl. dl is our source, and remember, you're integrating over your source because each individual piece of source contributes to the field at the point P. Okay, and so when you're integrating around a circle, we should not be surprised to get a factor of 2 pi out. Okay, so we will get a factor of 2 pi. That's just some intuition leading into perhaps how the integration is going to go. Now, how to handle the dl cross r hat. This is one of the two most crucial points. A lot of people would not have too much trouble getting here, okay? Because you can define your r vector from the point at which you choose your dl to your field point. That's fine. Your r hat vector is just going to be the unit vector along that direction. You can use the Pythagorean theorem to find the magnitude of r. The magnitude of r, this length, must be equal to the radius squared plus this leg squared, square rooted. So that's fine. But what do we do with this? Okay, this may not be the most intuitive part of this. Well, remember that dl goes in the direction of your current. Okay, dl goes in the direction of your current. So dl is going to go this direction. Okay? If we rotate our loop such that it is perfectly flat with our line of sight, that's equivalent to saying the current is going into the board at that point. Okay? And let me see if I can get creative here. That's almost exactly perfect length. I didn't mean to do that. That's really cool. So imagine that this marker represents my dl vector. Okay, so my dl vector is going into the board at this point. My r vector lies like this, right? So I have dl into the board and my r vector lying along my markers. What angle does this make? You can rotate it and you can see that it's a right angle, okay? So dl and r make a right angle with one another. So this angle right here is a right angle, and that's in contradistinction to this angle that r makes with the y-axis. Okay, those two angles are not the same. But this is the angle between dl and r hat, and it turns out it's 90 degrees. So what that means is that dl cross r hat, we can write this once again as dl magnitude times r hat magnitude times the sine of the angle between them. I don't want to use theta here because we might use theta for something else. I'll use alpha. Okay, so we'll label this right angle right here as alpha. And if I do that, then the sine of alpha is 1, the unit vector's magnitude is 1, and so this just becomes the magnitude of the dl vector, and that's just dl. Now here's one of the tricky parts. Okay, so this is just the magnitude of dl. Here's the tricky part. What about the unit the direction of the magnetic field? What is the direction of this cross product? Okay. Well, using the right-hand rule, if L goes into the board, dl goes into the board, and my r vector goes up like this, then my magnetic field is going to point like this. Okay? So my magnetic field is going to be at a right angle. And what color do I want to use? I'll use black. I didn't necessarily want to use black, but we'll use black. So your R vector, or I'm sorry, your magnetic field vector is going to come off like this. And I'm going to label it dB because this is the differential magnetic field contribution from this differential element. To get the total, we would need to integrate, all right? But this will always be at a right angle, okay? That's the crucial point. And that right angle comes right out of the cross product. The result of a cross product will always be perpendicular to the two components. So in this case, you can think of your DL is this way, and DB is going to be perpendicular to that, and R is this way, and DB is perpendicular to that, okay? Now, but what this means is that my contribution from DL is pointed in this direction. But if I looked at a contribution from this side, I would be pointing in this direction, right? So if I do the exact same thing and look at a similar DL over here, and now remember DL is pointed in this direction, and I do the exact same thing, draw the exact same R vector here. Ooh. Okay, there's my other R vector. And in that case, the dB from this current element is going to be this way. And once again, that will be perpendicular, okay? So what you can see here is that as you integrate around the circle, each contribution is going to eventually sweep out a cone, right? You're going to sweep out a cone. And what is going to happen is all of your horizontal, the components in your horizontal plane are going to cancel out. And you can see that from here because you have a horizontal component this way and you have a horizontal component this way. And to within my art skills, those arrows should be the same, right? So this would be dB in the XY plane, and this would be dB in the XY plane. And those two components are going to cancel. Only your vertical components are going to add up, right? So my vertical components are what are going to add up. And if we look at our vertical components, what are those components going to be, right? Well, it depends on what angle you want to use, but if we use this angle right here, let me use black. If we use this angle right here, okay, and we'll call this angle theta, right? Then this angle will also be theta, right? And we'll denote this as Z here, right? And this angle is also theta. So if this angle is theta and it's the vertical contributions that add, then those are going to be the sine components. No, I'm sorry. Those are going to be the cosine components, right? The sine components are going to cancel, so you're going to get the cosine components. So this turns into, this integral, right? This integral turns into, in this case, B is going to equal mu naught I over 4 pi a squared plus z squared times the integral of dl, after we've reduced the dl cross r hat to be just the magnitude of dl, times the cosine of theta, right? Because the cosine components are what is going to add up here. But the cosine of theta is just a constant, so the cosine of theta can also come out. But what is the cosine of theta? So the cosine of theta is going to be z over r, right? And since we're working in magnitudes, right, the cosine of theta doesn't care what direction r hat is, or what direction r is pointed in. It just cares about the magnitude. So cosine theta, in this case, is just going to be z over r. So I'm going to get another factor of the square root of a squared plus z squared. Okay, I'm going to get another factor there. And so this turns into mu naught I 4 pi a squared plus z squared times the cosine of theta, which is z over r, or z over a squared plus z squared to the 1/2, okay? And then still the integral of dl, right? But what is dl? dl is just an element of the length around the wire, so when I integrate around dl, I just get the circumference of the wire, or 2 pi a, right? So the integral around the wire just becomes 2 pi a, and doing all of this, right? Let's see, so 2 pi's cancel out. And this is going to be left with a factor of 2. And let's see. This is going to and if I remember right, I believe that result's correct. I was having a moment there. But yes, that should be correct. Okay. Something still doesn't sit right. I'll find it. Yeah, that something is not quite right. What is that something? I'll find it, and then I will correct it in the next video. But for now, that at least gives you a sense of where to put things in the Biot-Savart law and how to go from here into something that is actually integrable. Okay, so I'll find it and I'll update you. All right.